Hello, we're going to take a look today at an example of a probability using probability trees to examine a medical example. This is going to be using some conditional probability here. This example is based on some actual events. These are actually some friends of mine that were considering this back in my graduate school days. So this is the kind of thing that this friend of mine was looking at to help make some decisions. Cystic fibrosis is a genetic disease that's inherited by a double recessive trait. So what that means is it's carried on a particular gene. So each person will receive this gene, one from the mother, one from the father, and the gene could be either good or bad from each parent. The only way that you can actually get the disease is if you get the bad gene from both parents. If you get a good gene from one parent, a bad from the other, you're a carrier for the disease. You don't actually have the disease. You're perfectly healthy from this disease. But you can possibly pass the bad gene on to your offspring. Of course, if you got both good genes, there's no way you can pass this disease on. Your children will definitely not have it. So this friend of mine was a healthy man, and his parents were healthy, but he had a sister with cystic fibrosis. So if you think about that a minute, you'll realize that since his sister received a bad gene from both parents, this man's parents both are healthy, so they both have a good gene, but they also had to both be carriers. So both of his parents have a good gene and a bad gene. One of them at least gave him a good gene, but we don't know whether the other one gave him a bad gene or not. So let's look at this, and first of all, let's look at this situation. So, assume that two healthy parents are carriers for this disease, and make a probability tree showing the possible relevant genetic outcomes from the offspring, good and bad genes. And then what's the probability that a child will have the disease, and what's the probability that the child will be healthy but a carrier? And of course the third one is what's the probability that the child is completely free of the disease. Go ahead and figure that out now. Press pause now. Okay, so we're looking at this tree where we have two healthy parents that are carriers for disease. Each one of them can pass on either a good or a bad gene. So this is going to be a two-stage tree. The first one is you can either get from the father a bad gene from the father or a good gene from the father. Each has probability of 1/2. We know he has one of each, and the probability is 1/2 that he'll pass on the good one or the bad one. Each is 1/2. Likewise, we know the mother has a good gene and a bad gene, so really independent of what is happening for the father's gene, the mother can pass on with probability 1/2 a bad gene or a good gene in either case, regardless of what the father did. So we can multiply these probabilities. The probability that the father passed on a bad gene times the probability that the mother passed on a bad gene, given that the father did, that's 1/2 times 1/2 is 1/4. And similarly, all these paths are 1/4. We have 4 equally likely outcomes, that is bad, 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 good, good, bad, and good, good for the genetic makeup for this particular disease. So that means 1 out of 4 will be good, good. That means the person is healthy, at least in terms of this particular disease. They do not have it, and not only do they not have it, they don't have a bad gene at all, so there's no way they can pass this on down the genetic line. 1/4 of the time, these children will have 2 bad genes, which will make them double recessive. That means they will actually have this disease, cystic fibrosis in this case. And then 1/4 plus 1/4, or 1/2 of the time, the child will get both a good gene and a bad gene, making them a carrier for the disease. So the probability the child has the disease is 25%. Probability of a healthy child is 3/4 or 75%. Probability the child's a carrier is 1/2, 50%. And the probability that the child has no bad gene at all is 25%. So the first question would be, if you know you're both carriers, would you risk having a child knowing that there's a possibility that they could have this disease? The probability of the child having the disease is 25% there's a 75% that they will not have the disease. Is that 25% chance of a child with the disease enough to deter you from having children? What's the probability that this man is a carrier? See if you can figure that out. Press pause now. Well, notice that for the parents, they're both known to be carriers. 1/4 of the children will have the disease. 1/4 will be completely free, and 1/2 are healthy but carriers. Well, we know the man doesn't have the disease, so he now comes from that 3/4 group of the children that do not have the disease. 2/3 of this group are carriers, and 1/3 are completely free. So the probability that he does not have the disease, but he is a carrier, is 2/3. So in other words, the outcomes good, 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 bad, and bad, good for his genetic makeup are equally likely, and 2/3 of these are one good and one bad, which is a carrier. So notice we have some given information that he doesn't have the disease. So that means that we've eliminated that possibility of bad, bad. Now, there's no family history of the disease in his wife's family. She's Caucasian, and the probability of a healthy Caucasian from the United States being a carrier is approximately 1/20th. So, which is higher than it is for some other races, but 1/20th, at least I was told this, was the probability that a random Caucasian is a carrier. The couple was considering having a child. So given the information that we have so far, so we know that the man's parents are carriers. We don't know anything except about the mom, except she's a healthy Caucasian from the United States. What is the probability of the different genetic makeups for the children of this couple? And what's going to be the probability that they have a child with the disease? Go ahead and figure this out. Press pause now. Well, if we make a tree here, this is going to be a 4-stage tree. The first stage is going to decide whether the father is a carrier or is free of the disease. Same way for the mother for the second stage. Then once we've decided that, we can go on to decide what gene the child will get from the father and what gene from the mother. So C is going to stand for carrier, F is free of the bad gene, B is a bad gene, G is a good gene. We're just going to keep track of what's what at each level. So notice at the first stage we're choosing whether the father is a carrier or free. And there's a 2/3 chance that he's a carrier and 1/3 chance that he's free. So those are the labels on that first branches. Now, independent of that, the mother's chances of probability of being a carrier is 1/20th. So we get the mother could be a carrier or free of the disease, and those probabilities are 1/20th, and then the complementary probability of 19/20th, and for being free, and then the same thing whether the father is a carrier or is free of the disease. So that explains the second stage here for the mother. Now, once we look and see what could happen from the gene from the father. Now, remember in this top branch, the father is a carrier, so he could produce either a bad or a good gene to pass on to the child. Similarly, the mother is also a carrier, so she could also pass on a bad or a good gene. Each of those bad or good is probabilities 1/2 on those possibilities. Now, if we go down here where we have carrier then free, the father is a carrier, so he could produce a bad or a good gene to pass on to the offspring. But the mother's gene is definitely going to be a good gene, so with 100% probability or probability of 1 that will happen. On the other hand, if we're down here on the lower branch where the father is free, regardless of whether the mother is a carrier or free, the probability that the father will produce a good gene is 1. And in the case where the mother is a carrier, then she can produce a bad or good gene to pass on to the offspring. Down here in the very bottom where we have free, then both the father and the mother have good genes, and there's a 100% chance that they will pass on good. Both of them will pass on a good gene to the offspring. Okay, So these are conditional probabilities, and we can multiply all of these out to get probabilities. So if we take the top branch, top path, that's 2/3 times 1/20th times 1/2 times 1/2 reduces to 1/20th. 2/3 times 1/20th times 1/2 times the 1/2 here is also 1/20th. Similarly for the next two. This one down here is carrier, free, bad, good. Those are probabilities 2/3, 19/20ths, 1/2, and 1. Multiply those four numbers together to get 19/60ths, excuse me. And then the next one is also 19/60ths, probabilities of 2/3, 19/20ths, 1/2, and 1. Third one from the bottom, free, carrier, good, bad. Probabilities are 1/3 times 1/20th times 1 times 1/2 is 1/20th. Similarly for the next one, and the last one at the bottom, where we have free, free, good, good, that's 1/3 times 19/20ths times 1 times 1 is 19/60ths. The only one out of all of these that turns out to be have the disease is the one at the top, where it's bad, bad, which has to come from the mother and the father both being carriers, which is a 1/120 probability. The purple ones are the ones that ended up with a good and a bad in one order or the other, and those are carriers for the disease. They're actually this 1/120, 1/120, 19/60, and 1/120. And these, we can add these up. If we add all these numbers up here at the end, of course we're going to get 1. If we add just the purple ones up, we'll get the probability that it's a carrier, the child is a carrier. And the blue ones are possibilities where we ended up with two good genes, the 1/20th, the 19/60th, the 1/20th, and 19/60th. Add those together to get the probability that the child has both good genes. So if we put that together, the probability that the child will have the disease is the only one at the top where it was bad, bad, and that is 1/120, or 0.83, actually with the 3 repeating, %. So less than 1% chance that the child will have the disease. Probably the child will be a carrier of the disease, but not have it, is 41/120, or 34.17%. And the probability that the child will be completely free of the bad gene for the disease is 13/20, which is 65%. Now we get to the questions. A genetic test existed to determine if one or both of the parents are carriers. Now if they don't take these tests, then we're back to looking at these probabilities, or this probability tree here, to lay out all the possibilities. But of course there is a pretty good chance that the man is a carrier, but a very low chance that the wife there is a carrier. So the probability is high, 2/3, that the man will test positive and be a carrier if they take the test. Probability is low, 1/20, that the mother will test positive and be a carrier. If either one tests negative, then of course that means that neither one is a carrier, and there's a 0% chance of the child having the disease. However, if they both test positive, then there's a 25% chance that the child will have disease. Now at the time they were worried that the insurance company was going to say that if both parents were known to be carriers and they went ahead and had a child that turned out to have the disease, that was considered a pre-existing condition and the insurance wouldn't pay out. So here are the questions that this man had, this friend of mine. Should they test the man, or should they test his wife, or both, or neither? And what would they decide to do? Should they decide to not have a child based on this information, or should they decide to go forward? It's pretty interesting questions, and so looking at these probabilities help make some decisions for them. What they ended up deciding to do was to not have the test and take their chances on less information. they decided that the probability was very low that the wife was going to have the be a carrier, and so the chances of probability of the child having the disease are extremely small. Okay, less than 1% as we figure this out. So they decided to go ahead and take their chances, have the child. They did have at least one child that I know of who turned out to be free of the disease. Of course, they could have found out more information. The worst case scenario for them would have been that both of them tested negative, both of them tested positive and actually had the disease. And so, but even in that case, there was a 3/4 chance, 75% chance that the child would still be healthy. And they never quite got to that point of testing, but they were wondering, well, maybe they would even take their chances even on that, because there's still a 3 out of 4 chance that the child would be healthy. So in any event, the basic point of this exercise is just a little exercise to practice with some probability trees, but it's also showing how these can be used in real-world situations. A medical example was chosen here because over half of the students in this class are pursuing a degree in some form of medical field. So here's a very good real-world example that we can all relate to, that looking at probabilities might help us understand what's going on a little bit better and help us lead us to making better decisions.